In the next set of videos, we're going to look at conservation of momentum. Conservation of momentum is the first of the conservation laws we come to in this course. Much like conservation of energy, conservation of matter, which you talked about in chemistry, a conservation law is basically meaning that the total amount of something is going to stay the same within the system. For momentum, the conservation of momentum means that the total momentum of all the objects in the system we are looking at will remain the same as long as there's not some sort of external force on the system, or the external forces on the system are not changing. This must be a closed system, meaning that the total system, all the objects that we're looking at, do not gain or lose mass overall through the course of the collision explosion that we are looking at. The best summary of the conservation momentum is sigma pi equals sigma pf. Sigma, meaning sum of, mathematically, the sum of all the initial momentums of every object in our system is equal to the sum of the final momentums of every object in our system. Now, there are three separate cases we want to look at with conservation of momentum. We want to look at the case where objects collide and bounce off one another. We want to look at the case where objects collide and stick together. And we're going to look at the third case known as explosions, where an object starts stuck together and moves away from each other after the explosion. The fourth video in this series will be a mixture of those three types of example problems to allow you to start to see how you would recognize between the three. The first type we're going to look at is called elastic collisions. Elastic collisions are these perfectly bouncy collisions, meaning that objects hit off of one another and move off with no loss of energy. So one object collides with a second object, and the objects move off in a way where they do not lose any energy. The formula, sigma pf, sigma pi, can be written out in this case. You could think of this as pi for object 1 plus pi for object 2 equals pf for object 1 plus pf for object 2. Since p, momentum, is mass times velocity, you see it written out this way. So let's look at some examples of elastic collisions. An 8-kilogram ball traveling at 9 meters per second to the right strikes a 5-kilogram ball at rest. The 5-kilogram ball travels to the right at 4 meters per second. How fast is the 8-kilogram ball moving? So let's write out everything that we know here. We have object 1 and object 2. This one has a mass of 8 kilograms, has an initial velocity of 9 meters per second, and we are trying to find its final velocity. Object 2 has a mass of 5 kilograms, has an initial velocity of 0, and a final velocity of 4. Now, we can set up the equation m1 v initial 1 plus m2 v initial 2 equals m1 v final 1 plus m2 v final 2. Plug in our values. 8 times 9. The 9 and 4 are in the same direction, which we're making them both positive. 5 times 0 equals 8 times vf1 plus 5 times 4. 8 times 9, 72. 5 times 0 is 0. Equals 8 v final 1 plus 5 times 4, which is 20. So 52, subtract 20 from both sides, equals 8 v final 1. Move it up here. V final 1 equals 52 divided by 8. So 52 divided by 8 is 6.5. Meters per second. So this one would move at 6.5 meters per second to the right. Okay, try these remaining problems on your own before continuing the video and watching me complete the problem. 3-kilogram baseball traveling at 18 meters per second strikes an 80-kilogram catcher on ice and rebounds at 12 meters per second. How far will the catcher travel in 2 seconds? So, we're getting a little bit more complicated here. We have the baseball and the catcher. Baseball has a mass of 3 kilograms, an initial velocity of 18 meters per second, a final velocity of negative 12 meters per second, because it bounces back, so I have to make that negative. Catcher has a mass of 80 kilograms, an initial velocity of 0, catcher's just sitting there, and we need to figure out its final velocity, and then in the time of 2 seconds, we need to figure out the displacement. It's on ice, so he'll move at a constant speed once he's hit. So we're going to start with our equation, m1 v initial 1 plus m2 v initial 2 equals m1 v final 1 plus m2 v final 2. m1, 3, v initial 18, 80 times 0 equals 3 times negative 12 plus 80 times v final 2. So now we need to solve this. 3 times 18, 54, plus 0 equals negative 36 plus 80 v final 2. So add 36 to both sides. 90 equals 80 v final 2. V final was 1.125. And since this is traveling at a constant speed, v equals delta x over t. 1.125 equals delta x over 2. Catcher will travel 2.25 meters. Okay, another problem. Football player runs at 8 meters per second and plows into an 80-kilogram referee standing on the field, causing the referee to fly forward at 5 meters per second. If the collision causes the football player to stop, what must be the mass of the football player? So we have the player and we have the referee. Player, we don't know its mass. We know its initial velocity is 8 meters per second. Its final velocity is 0 meters per second. The referee has a mass of 80 kilograms, an initial velocity of 0. He goes flying forward at 5 meters per second. So m1 v initial 1 plus m2 v initial 2 equals m1 v final 1 plus m2 v final 2. So mass 1 is what we're trying to find, times 8 plus 80 times 0 equals mass 1 times 0 plus 80 times 5. So mass 1 times 8, 80 times 5, 400. You get a mass of 50 kilograms. Okay, that takes us through examples of elastic collisions where two objects are bouncing off one another and the momentum is conserved. So the total momentum before the collision and the total momentum of all the things after the collision are equal.